All right, I just want to go over just kind of a more complicated problem involving inclines here with friction and with inclines and with some kinematics involved as well. So this is going to be kind of an all-encompassing problem. If you can do this problem, you can do any problem. But the thing I really want to stress is that the rules stay the same. So keep using the structures that we've built in, keep using the kind of templates that we have, because as long as you're doing that, just because we change kind of the initial kind of setup, it doesn't change the template that we use. Just because we change what it looks like application-wise doesn't mean that we change the rules that we're using to solve these problems. So make sure that before you watch this video, you've at least attempted to do the problem and solve for some of these values. And as you kind of fill in your information, you're going to realize that you know how to do this problem. It's just a matter of ensuring that you are using the rules properly that we've talked about. So first of all, we've got an incline here. It's a 30-degree incline, and we've got this block, but the block is moving up the incline. All right, so this is 30 degrees. And the block is going to be moving up the incline. Now, there's nothing pushing it up the incline. It just already had a speed going up the incline. So don't draw a force up that incline. There's nothing pushing it up the incline. It's just moving up the incline. And we want to make sure we remember the rule. Just because something's moving a certain direction doesn't mean that it has a force pushing it in that direction. So let's talk about the forces that are acting on this block. We should have a force of gravity straight down. We've got a normal force. We've got a force of friction. Now the block is sliding up the ramp, so the friction is actually going down the ramp. The friction goes down the ramp. So let's talk about kind of what that looks like in terms of our components of gravity. So I've got my perpendicular component and I've got my parallel component. And again, remember, this is 30 degrees. This is 30. That's small. So that's 30 degrees right there. So what I want to make sure I can do first is I've got my free body diagram. I've got F net, M, and A. So once I have that set up, I can just start to fill in the values that I already know. So I know that the block is 5 kilograms, which means that this is 50 newtons. Now I need to know my sine and cosine of 30. So I need to find my parallel and perpendicular components. I need to find my parallel and perpendicular components. So I'm going to do that. Sine of 30, sine of 30 is 0.5. So this component here is 25 newtons. That's the parallel component. So let me kind of label that over here. FG parallel is 25 newtons. I also know that my FG perpendicular is cosine of 30 times 50, so that's 43.3. 43.3 newtons, 43.3 newtons. So now I've got my components here. I've got my parallel and my perpendicular component. Now remember, this parallel component is still going down the ramp, and then we still also have friction going down the ramp. Then we've got our normal force, and we've got our perpendicular component of gravity. So if I think about the free body diagram like this, then it becomes pretty clear, well, these two components are the same. So my net force is really just those two components added together, which is FG parallel plus my force of friction. And since it's sliding, it's going to be my kinetic friction, which means that I need to find that force of kinetic friction. Now I know that my force of friction is mu times my normal force. And it's very important that you recognize that the normal force is the perpendicular component the perpendicular component, right? We said those were equal, the normal force and the perpendicular component. It's not the force of gravity. Again, another reason why we make sure that we are not using the force of gravity in our friction calculation. It's the normal force. So 0.25 times 43.3 gives you 10.825. So my force of friction is 10.83 newtons. So this is 25 newtons. This is 10.8 newtons. So my net force is 35.8 newtons. Now, my mass is 5. That means my acceleration, so if my speed is 10 meters per second, I'm going to allow that to be the case. So I'm going to say that up the ramp is the positive direction. That means acceleration is the opposite direction. So I'm going to make sure I remember that that is a negative value. That would be something unfortunate that to forget. So make sure you remember that component of the situation. Divide that by 5. My acceleration is negative 7.165 technically, but negative 7.2 meters per second squared. And then what I need to be able to do is figure out two different components, right? I need to use kinematics to find delta x, and I need to use kinematics to find t. So if I want to find t first, I know that my acceleration is negative 7.2, my initial speed is 10, my final speed is 0. So I can just
part are we going over?
do negative 7.2. Sorry, I'm making a video real quick.
Oh, sorry.
All good. I can do negative 7.2, and that will I divide 10 by negative 7.2, and that will give me the time, right? Because VF equals VI plus AT. My VF was 0, VI was 10, A is negative 7.2. So if I do that, I get 1.4-ish seconds, 1.39. And then I can use that to find delta x using using delta x equals VIT plus 1/2 AT squared. I could use VF squared equals VI squared plus 2AX. Let's just do that one. So when I use VF squared equals VI squared plus 2AX, I get 6.94 meters. So again, this is essentially what you're looking for here. You'll need to use some of these values in the second part of the calculations, but again, we're just kind of setting up our template, writing out the things we know, filling in our values, filling in the forces we can calculate, and once we do that, we're able to kind of figure out the important pieces of information that we can find. Hope that helps. See you guys later.